Welcome back to Very Ordinary Differential Equations. In this lecture, we continue studying applications of first-order equations, moving to a study of pendulums, but again, undamped pendulums. Well, how does Newton's second law translate to a pendulum system? So we have a mass m, and it's the end of a rigid length capital L, which rotates around a central point. Okay, Newton's law still applies. Force is mass times acceleration. But if gravity pulls straight down and our object is rotating around some axis, how does that really play out? So here's our system. Okay, we have gravity pulling straight down, but our mass is at the end of something of length L, and y is going to represent that angle here. Now the acceleration really depends on the angle between the pendulum and the downward gravitational vector. For example, if the pendulum is just hanging straight down with no initial velocity, gravity isn't going to do very much. It's just going to pull straight down, but I'm already pointing straight down. On the other hand, if I'm all the way out here at a 90-degree angle, gravity pulls very much on the pendulum. What we end up with is the mass times the length of the rod or string times the acceleration is negative mass times gravity times the sine of the angle. Okay, so it makes sense that a sine of the angle would show up here. When this angle is 0 and I'm pointing straight down, there's no acceleration. When the angle is 90 degrees or pi over 2 radians, my sine is at its maximum and I have my maximum downward pull. This can be simplified by dividing the m out of the entire expression and moving the L over to the other side. Y double prime is negative g over L sine of y. So here's the differential equation we have for our undamped pendulum. I say undamped because the only force acting is gravity. There is no air resistance in this situation. We can make our same substitution, okay, where y double prime, instead of calling it dv dt, we call it v of y times dv dy. So v times dv dy is negative g over L times the sine of y. Now dv dy is the change in velocity as the angle changes. Remember, y represented our angle. Okay, so this is our angular velocity. We can integrate both sides. Okay, this is separated now. On the left, I can call this v dv, and on the right, negative g over L times the sine of y dy. So we just get v squared over 2 equals g over L times the cosine of y plus some constant of integration. So we've managed to integrate and got v squared over 2 is g over L times the cosine of y plus a constant. Remember, y is our angle. Now let's suppose at time t equals 0, we have an angle of 0. So I start off pointing straight down, and our initial velocity is given by v naught. Then what we can solve for is that c must be v naught squared over 2 minus g over L times the cosine of, well, 0. If y naught is 0 and v naught ends up over here, then c is solved for just as follows. Of course, the cosine of 0 is just 1. So I can plug this choice of c into our original expression, and we end up with v squared over 2 equals g over L times the cosine of y plus c, where c has been solved for to be v naught squared over 2 minus g over L. All right, so with our initial conditions of hanging straight down with some initial velocity, here's how we've solved things. We can factor a little bit and just simplify our expression. And now, instead of calling this 1 minus the cosine of y, we can call it 2 times the sine squared of y over 2, using one of our half-angle identities. So a half-angle formula has gotten us here. Now for convenience, I'm going to denote v sub c to be the square root of 2g over L. That allows me to replace 2g over L with vc squared. Why would I want to do that? Well, this term is now something squared times something squared. It's definitely a positive number. So I have v naught squared minus something positive. What we see is that v squared is definitely less than or equal to v naught squared, regardless of the angle y. Now, how could v squared equal v naught squared? The only way that v squared could equal v naught squared is if sine squared of y over 2 is 0. In other words, if the sine of y over 2 is 0. Now, y represented an angle as our pendulum rotates around. So y is in between 0 and 2 pi. Therefore, y over 2 is between 0 and pi. The only angles at which the sine of y over 2 is going to be 0 is right at y equals 0, or coming all the way back around to y equals 2 pi. So the only way that our current velocity can actually equal our initial velocity is when y equals 0, when we are at the bottom. So in other words, our velocity cannot exceed in magnitude our initial velocity. The maximum angular speed is the initial angular speed, which happens when you are pointing straight down. And this makes great intuitive sense. As our pendulum rotates from pointing straight down, it's moving up. It's going to slow down. The fastest the angular velocity ever gets is when it is at the bottom. That's what we've just solved for. The only way v squared can be as large as possible, the initial velocity, is when our angle is 0, when we are pointing straight down, when we've come back to the bottom. So here's the solution we've already derived. But now let's make another assumption. Let's presume that vc squared is less than v naught squared. Now remember, vc is some constant. V naught, however, is our initial angular velocity. So we're assuming our initial angular velocity is pretty big compared to this constant. Looking back at our solution, sine squared cannot be any bigger than 1. So I have v naught squared minus something. Okay? What is the smallest this could be is when the thing I'm subtracting is big. Now the biggest this can be is when sine squared is 1. So the smallest this can be is v naught squared minus vc squared. If I make this assumption, then v naught squared minus vc squared is positive, meaning v squared is always positive. Well, if v squared is always positive, it is certainly never 0. Now, if v is continuous, a very reasonable assumption, then it never changes sign. It can't go from positive to negative without going through 0, and we've just seen that our angular velocity will never be 0 under this assumption right here. So our angular velocity is either always positive or always negative, and it has a fixed positive minimum, the square root of v naught squared minus vc squared, because this can't exceed 1. So under this assumption, our object has a fixed minimum velocity, and it's either always positive or negative. That's to say, if you make the initial angular velocity big enough, it will simply spin in the same direction forever and ever. Also observe that your minimum angular velocity will happen when sine squared of y over 2 is as big as possible. In other words, if y is pi, because then the sine of pi over 2 is 1. That's as big as this can possibly get. Y equals pi represents pointing straight up, because remember that y was our angle from downward. So regardless of how I set my object in motion, if I set it with initial angular velocity big enough, it will spin around in one direction forever, and when it is pointing up is when it has the slowest angular velocity. Again, this is all very intuitive, but thankfully our solution matches how we expect these systems to behave. Once again, here's the solution we've derived. What if, on the other hand, our initial velocity is less than this constant? Well then, if this quantity is pretty small compared to this one, there will be y's, or angles, that correspond to when our velocity is 0. And you can solve for that choice of y, and it's just going to be 2 times the arcsine of the absolute value of v naught over vc. If your angular velocity reaches 0, then your mass has stopped, and then gravity will pull it back down. And we've just determined the angle at which the angular velocity is 0, and that's where it stops. So between plus or minus these two angles, having come around and reached this angle, it comes back down, and we'll go back up to that, and then come back down, and so forth. So if our initial velocity is small compared to some constant, our pendulum has to oscillate back and forth between 2 fixed angles that we can explicitly solve for. Again, here's the solution we found. What if, on the other hand, vc squared is exactly equal to v naught squared? In other words, they're plus or minus equal to each other. Well then, for exactly y equals pi, this will be 1, and then this will be 0. So when y equals pi, the object is pointing straight up and gets a 0 angular velocity. Well, what happens then? We've set our object with some initial velocity, and as it rotates, it slows down until it exactly stops when it's pointing exactly up. It's not a particularly realistic situation. In practice, your initial velocity is going to be ever so slightly off. It's either going to be slightly higher, in which case our pendulum swings around and around forever, or slightly lower, in which case it oscillates between two fixed angles. So altogether, what have we now seen? We applied Newton's second law to the idealized situation of a pendulum, a mass at the end of a rigid length which rotates around a fixed point. There were also no damping forces. The only force acting on our mass was gravity. There's no atmospheric resistance, for example. What we saw is that depending on the initial angular velocity, a few things might happen. If your initial angular velocity is big enough, the mass spins around forever. Or if it wasn't big enough, it will oscillate between two fixed angles. Technically, there was a third possibility where perhaps the mass rotates and exactly comes to rest pointing straight up, at which point it will stay there forever. But that was not a very realistic situation. It relied on a certain initial velocity being exactly correct. And exactness is never quite going to happen in a real situation.